Afternoon, everyone. I hope that you were able to enjoy some of the sunshine that's out today. What a beautiful day. Before we get into our lecture, I wanted to make an announcement. Now, I know that some of you have been quite concerned about this transition from face-to-face classes to online lectures. I can fully appreciate all of the concerns that you've had. As you can imagine, I've also had similar types of issues to deal with in trying to give these lectures and getting them prepared in an online setting. So I also appreciate the patience that you've had with me with respect to this transition on my end as well. Now that test 3 is done, we are, they're in the middle of getting graded by the TAs. So we'll have finished test 1, test 2, test 3, and all of the assignments except for the last one's out. Now that one I've made due on this Thursday evening at midnight, mainly because Friday is Good Friday. I don't want to put something due on a holiday. If you're really strapped time and you want to get it in, but you need a bit more time, then let me know. We can deal with that. But the bigger question is your final assessment. So what I wanted to discuss with you was having an optional final exam for this course. What that means is that there are two options. One is having your entire course grade based on just your assignments and the tests. The way that would work is that your assignments would still be the best 7 out of 8 assignments, and they would be worth all of them equally weighted with a total of 40% of your final grade. Your tests, so your test 1, test 2, test 3 would then be equally weighted, so 20% each, and worth 60% of your final grade. Particularly if you are perhaps on the lower end of you're wondering whether you can actually pass the course or not, so you'd like to have the final, there is still that option as well. In which case, it would be what I announced after the university-wide closure of classes. So in that case, the assignments are still the best 7 out of 8, and then that would make them worth 30% of your final grade. The tests are still equally weighted, so the 3 tests would be equally weighted and worth 50% of your final grade, and then the final exam is worth 20%. I will have to think about those of you who missed one of the tests and was having that weighted to the final exam. But these are the two options that stand at the moment. And the way it works is that you need to decide before you write your final exam which option you would like. If you write the final, so this is a key point, if you write the final exam, then you will automatically be assessed for by option 2. So if you don't want your final to count, you need to decide that before you write the final exam. Okay. And what else? So, right, you have this option 1 or option 2. Whichever option you choose, by when grades are announced, you will still have the choice at the university level of whether you're assigned a numerical grade for the course, a pass, or a withdrawal or a drop. So you can decide that after you see your grade, that the grade that you see will be based on either option 1 or option 2, which needs to be decided before the final exam. The last item that I wanted to mention, so we have assignment 8 due Thursday at 11:59 p.m. And for final exam, I need to double check what the date is for that. It should have been released on WebAdvisor. I saw it briefly on Friday, but then when I went in again on the weekend, I couldn't see it. I don't know if that was a technical glitch on my end, so I still need to double check with WebAdvisor. If you've seen it as well, you can feel free to take a screenshot, post it on the discussion board. But the final exam, I believe, is closer to the end of April. It is not exactly 1 week from the original schedule, which is what the university had been saying when the university first closed down. So they had to come up with a new schedule to accommodate the online setting and students who are in SAS. And so there were a number of logistics they had to work out on their end with scheduling. I will post what the new date for the final exam is soon, hopefully by the next lecture. Okay, so I will again write this out as an announcement on CourseLink and send it out in an email, but this is the first news that you're getting it here. Okay, so last topic of the course, logistic regression. Remember, in logistic regression, what we're doing is running a regression model where the response is binary. And so in our regression model, what we actually do is not model the binary response itself, but we model the log odds or the log of P1 minus P, where P is the probability that X equals 1. That Y, our response variable, equals 1. So here's the regression model, log of P over 1 minus P. So the log odds is equal to beta naught plus beta 1. There's only one X when we're dealing with simple logistic regression, which is what we've been discussing up till now. We'll talk briefly about multiple logistic regression next lecture. So just to sort of recap, last day, we were looking at this SALT and CVD or cardiovascular disease example. We showed that in terms of interpreting the model, the log odds for those on the low salt diet is given by beta naught plus beta 1 when we let X equal 1 represent the low salt group. So X is essentially a dummy variable here or an indicator variable where 1 is indicating the group of interest. And then the high salt group is where X equals 0. So when we plug in X equals 0 up here, then we get that our log odds of CVD for the high salt diet group is simply beta naught. Okay, so why am I recapping this? Because what we wanted to do was come up with an interpretation of our model parameters. Just to remind us what those values were last day. Let me see, I somehow froze this. See if I can unfreeze it. There we go. Okay, so what we did last day was say, given the data or the counts that we had for each group in our 2x2, or I should say in our table with CVD and low salt, high salt, then we came up with a logistic regression model where the log odds of estimated odds was equal to minus 2.135 minus 0.193 times X, where X is our salt status. And we said, if we go through to interpret this, then we need to interpret these two parameters in terms of the log odds, which is something that's rather difficult to do, or for the general public to sort of grasp. So instead, what we try to do is provide an interpretation that is of the odds themselves, or an easier function of the odds to understand. So that's what I wanted to look at today. Now, when we actually calculated, say, this B1 term, what did we do? We looked up, going back to the top, the log odds of odd minus B naught, where B naught is the log odds for the high salt group. So in other words, I'm going to move forward. Now, depending on when you downloaded the slides, the next page for you might say 163. There was something wrong in my latexing of these notes. So it should say 162. So it might look like what page 162 is missing. It's not, or you'll see that 162 is the same as 161. So please excuse that. So if we look at the log odds for the low salt group minus the log odds for the high salt group, what we have here is a difference in log odds. And for the low salt group, we just discussed how it was equal to beta naught, B naught plus B1, because we're talking about estimated odds here, minus the estimated log odds for the high salt group, which is B naught. And of course, if we take B naught, B1 minus B naught, we get back B1. But from a mathematical perspective, if you take different logs, that's equal to the log of the ratio. Okay, so what we have here is the log of ratio of odds. And how did we get that? We got that because, I'll write this on the side. Actually, you know what? It's probably easier for me to write it this way. Ln A minus ln B is equal to ln A over B. Okay, so if we take the difference of these log odds, then we can put it as a log of the ratio of those odds. And we know that that ratio, the log of that ratio is equal to B1. So in other words, the log odds ratio is equal to B1. And remember, what we wanted to try to do was provide an interpretation that was on the original scale. That's in terms of the odds themselves, not the log of the odds. So we can exponentiate both sides. If we exponentiate both sides, then the ln disappears. We're just left with this ratio of odds. And on the right-hand side, B1 becomes e to B1. So here, e to the B1 is an odds ratio, where the ratio is taken with the x equals 1 group on the top and x equals the x equals 0 group on the bottom. Okay, and so here we have another way to think about this in terms, going back to this idea of finding a nice interpretation. If we multiply both sides by odds high, now interpretation that compares the odds for the low group to that of the high group. So we can say that for the cardiovascular data, e to the B1, which happens to equal e to the minus 0.193, is equal to 0.824 and so forth. That quantity So E to the B1 is the odds ratio of developing cardiovascular disease for the low salt diet group relative to the high salt diet group. Or in other words, the odds of developing cardiovascular disease for the low salt group are reduced by a factor of 0.824 compared to the high salt group. So what if we had coded X differently? Okay, and I know it might be confusing for you as we go through this today because we're talking about how to interpret model parameters, and we're going through a number of different ways to word that interpretation. Part of that is because when you look in the literature, people will interpret this quantity in different ways, and they often mean the same way. It's the same thing. It's just some things are easier to understand in different contexts. So what if we had coded X differently, right? So we chose X equals 1 to be the low salt group. But someone else might say, oh, but low and high, we could do this as an ordinal variable where the low should be the 0 and the X equals 1 should be the high group. So what if we had actually done that comparison instead? Well, if we let X equal 1 represent the high salt group and X equals 0 represent the low salt group, then the fitted model would be the log odds equal to minus 2.315 and so forth. If you compare this to what you got for our original data, this is the exact same B naught. But now, because we've reversed the definition for X, instead of a minus, we have a plus 0.193. So here, sign of B1 flipped. It was negative, now it's positive because we've changed the definition of our indicated variable X to represent the other group. So well, now that we have a coefficient of B1 equaling positive 0.193, how do we interpret this? Then our odds ratio is estimated by the ratio of the estimated odds for the high group compared to the low group. It is still E beta B1, which now is positive instead of negative, and is equal to 1.213 and so forth. So before we had 0.824, and now we have 1.213. So the odds of developing cardiovascular disease for the high salt group have increased by a factor of 1.213 compared to the low salt group. And that interpretation by looking at multiplying both sides of this equation by the estimated odds of the low group. So we come up with this quantity here. Many times what you'll find is that in a paper, they'll actually say that 1.213 is the odds ratio of developing cardiovascular disease, comparing the high group to the low group, or something along those lines. But that's to say, and it doesn't matter whether you word it that way or this way, in terms of the odds ratio directly, or in terms of increasing or decreasing by some factor. So the main point for our logistic regression model is that when we go to interpret the model parameters, we want to do it in terms of the odds ratio directly, not log odds, but in terms of odds ratio itself, or the odds themselves. And what that means is that we need to exponentiate the model parameters. So for simple linear regression, we want to look at e to the b1. Okay, so that was where we were looking at an indicator variable. What if we had a quantitative explanatory variable? Then what happens? Instead of talking about this in the general setting, let's go back to a familiar example. Think back to the movie data example that you analyzed in assignment 6. And if you recall, there was a simple random sample of recent movies from the same year. The question of interest was whether a movie was going to be profitable or not. So in assignment 6, you looked at regressions of the total US revenue onto a number of other variants, one of which was the opening weekend revenue. So in example 14.6, they're looking at the same database, but they took a random sample of 76 recent movies from that year. And then they recoded or created the dummy variable y, or indicator variable, that equals 1 if the movie is profitable, where they'll say it's profitable if US revenue is greater than the budget. So in the software, you could easily code it, do a comparison. If the total US revenue for that movie was greater than its budget, Y gets a 1, otherwise it gets a 0. And now what we want to do is consider a simple logistic regression of this new variable Y with our explanatory variable given by the log of the opening weekend revenue. So when we get looking at what this will be called L opening. P is now the probability that the movie is profitable, because remember, it's the probability that Y equals 1 and Y equals 1 when the movie is profitable. The model is given by the log odds that the movie is profitable, which equals the log of P over 1 minus P, which is given by beta naught plus beta 1x. That's an extra bracket in there, or a misplaced bracket. So how do we actually estimate this? In general, you wouldn't do this by hand. We don't have a nice 2x2 table. We would actually rely on the software to fit the model. And from the software, we can estimate the log odds of being profitable based on our estimated probability of being profitable. And in this example, okay, I do have, even when I read through this, I didn't see these. So our estimates of the model parameters are given by B naught and B1. So our regression model is B naught plus B1x, where x is the log of the opening weekend revenue. And from the software, we can get that this is equal to minus 2.556 plus 1.125 times x. In that case, the odds ratio can be estimated by e to the b1, just as we did in the cardiovascular disease setting, which is e to the 1.125. So this is our b1 estimate. And that gives us an odds ratio of an odds ratio estimate of 3.08. So that's telling us that increasing log opening weekend revenue by 1 unit, or just say by 1, increases the odds that a movie is profitable by about 3.1 times. So every time that log of opening weekend increases by 1, then the odds ratio increases by a factor of 1.12, by a factor of approximately 3.1. Okay, so by this point in time, we've looked at a simple logistic regression model in the case where our explanatory variable is an indicator variable itself, in which case the interpretation is nice because it's just pairing our two different groups. But we've also looked at quantitative setting where the odds are associated with a unit increase in the X variable, whatever that is. But we're not done yet. Usually what we want to do is perform some inference on these model parameters. So how can we do that? Well, once we've fit the models in our software, it's actually analogous to what we've been doing all along. Our confidence interval for the slope beta 1 is equal to B1 plus or minus Z star times the standard error of B1. So it should be Z star standard error of B1. That's the margin of error. But again, here's the snag. Just as in model interpretation should be on the original scale, not in terms of log odds, but in terms of odds. We should similarly report our confidence intervals on the original scale in terms of odds, not in terms of log odds. So what that means is we need to exponentiate the confidence interval endpoints as well. So the confidence interval would not be, we generally don't report it for beta, but we report it for the odds ratio. So for e to the beta 1, and it's given by e to the B1 minus Z times its standard error, and the other endpoint becomes e to the beta 1 plus Z star times its standard error. To perform hypothesis tests, so for instance, the test that beta 1 is equal to 0 versus unequal to 0, we have a new test statistic. It's a chi-square test statistic. And the way we calculate it is similar to the t setting. We take B1 divided by its standard error. Now we need to square that. And the purpose of that is that under the null hypothesis that beta 1 actually is equal to 0, it can be shown that our new test statistic x squared has an approximate chi-square distribution with 1 degree of freedom. Okay, so when we're testing one model parameter or one slope parameter, it's associated with 1 degree of freedom. Okay, so testing for one slope parameter implies degrees of freedom equals 1. And then the p-value is a one-sided p-value, so, or an upper tailed test. So if this was x squared, area above it is equal to the p-value. Okay, even though it's a two-sided test, it's an upper tailed test, one-sided p-value. Okay, and what else? When you look at your software output, this test statistic x squared, it's often called a walled statistic. Okay, so why don't we look back at the salt and cardiovascular disease setting as well as the movie data, and just talk through the output and how we would build confidence intervals, perform tests and such from these SPSS output. So here's an example for the SALT and the cardiovascular disease. What we can see is that the output's similar to the other the simple regression and multiple regression settings that we've seen before. We have a column for the variables. This one here is saying that this is associated with the low SALT group. That was our X variable. So this is for X equals 1 and X equals 0. B, that's our estimate of our intercept and slope parameters, the corresponding standard errors. That's the Wald statistic that we were talking about. So our Wald statistic is given by B over standard error squared. Performing a test on our slope parameter. So this one is B1. And then the constant is always associated with B0. We have 1 degree of freedom for testing, and then we're already getting our upper bound p-value here. The two-sided test, but a one-sided p-value. And then as written up here, this is e to the b, so that is giving us the odds, or the estimated odds. Whereas this one is the b is the log odds. Okay, so what can we do with this output? If we wanted to build a 95% confidence interval for the slope, remember we simply have to take our estimate of the slope plus or minus a z value times the standard error. So one comment I should make here is that although we don't go into any of the theory or the background here, as soon as we look at this binary data, remember with proportions, we had to invoke our central limit theorem. When we do our hypothesis tests, we always use the Z value. Well, it's the same idea here. We have a binary response. We're relating it with explanatory variables. And instead of dealing with its distribution directly, we invoke some type of a central limit theorem. So all of our inference is now based on the normal distribution, and this is why we're using Z values. So the standard error, we've got our Z star times the standard error. If we're looking at a 95% confidence interval, then Z star is equal to 1.96. This we should know off by heart by now. We have our B1 that we can read off of our SPSS output. The standard error can be read off of the SPSS output. And then when we calculate our endpoint, the minus 0.193 minus 1.96, here's our value minus 0.484. And then if we continue our decimals, we would get 66668. And the upper endpoint will be 0.1098. Okay, so what can we see here? In this confidence interval, it's still, remember, it's hard to interpret because it's in terms of our log odds, not the odds themselves. So what we do is we find the 95% confidence interval for the odds ratio, not for beta 1, odds ratio. which means we need to exponentiate our endpoint. So here we have minus 0.485. We take e to the minus 0.485. And we also exponentiate the upper endpoint. This is now giving us an odds ratio of 0.616 to 1.103. I want to make a small comment here, a side note. If the odds of, say, low over odds high equals 1, then odds low equals odds high. Okay, so the special case that odds is equal to odds ratio is equal to 1, that means the odds in both groups are equal to each other. So there is no particular association. There's no difference between being in the low salt group or the high salt group. The odds of cardiovascular disease are the same, at least for CVD. So if we look at our odds ratio, we see that this interval covers the value 1. Remember before when we were trying to look at a difference and we'd say, hey, the difference covers 0, there's no significant effect or association. Well, now that we're talking about odds ratio, the magic number we want to compare to is 1, because when the odds ratio is 1, that's when there's no difference between groups. So looking at this odds ratio, I already know that were I to perform an hypothesis test for the odds ratio equal to 1 at the 5% level, then it would come up as not significant. Well, let's see, what does that mean? In the case of simple linear regression, testing whether the odds ratio is equal to 1 is actually testing whether beta 1 equals 0 versus beta 1 unequal to 0. So this two-sided test on the slope parameter. So note, if beta 1 equals 0, then odds are equal in the salt group and the low salt and the high salt group, i.e. OR is equal to 1. Our test statistic, remember the x squared one, is given by the square of the ratio of B1 over its standard error. Our B1, let me pull up our, well, if we look up here, we can see B1 was given by 0.193297. The standard error was given by 0.148658. When we take the ratio, we square it, and put it 3 decimal places, we get 1.691. And note that this 1.691, I'm just going to slide this page up, so you might have it in front of you, is exactly the value you get for your Wald statistic from your SPSS output. So here, the test is essentially already done for you. Under the null hypothesis, the degrees of freedom is equal to 1. And if we had to look up our p-value, it would be the probability that a chi-square random variable is greater, with 1 degree of freedom, is greater than or equal to our observed Wald statistic value, which is 1.691. To actually look that up, we would need to refer to table F. I'm just going to pull that up for us. So we want 1 degree of freedom, and we're looking at the number 1.691. Here is table F. Try to zoom this in a little bit more. And what we see, remember we wanted 1.691. So looking across the top, we have 1.62, 1.64, 2.07. So 1.691 is between these two values, the 0.15 and zero 0.2. We don't have to multiply by 2 or anything because this is an upper-tailed test. And so the conclusion that we come to is that our p-value is between 0.15 and 0.2. Now, of course, if we were looking at software, using software, we wouldn't have to go through this process because from software, we can look up a table where it says significance, and it tells us that the p-value is equal to 0.194. Conveniently, or I should say, it's good to see, comforting to see that the range that we got includes this 0.194. Okay, so this is the more precise value. But of course, for any reasonable alpha level, 0.194 provides us with evidence to reject our null hypothesis. Okay, the quantitative setting. When we look at the quantitative movie data example, our similar to what we had before, and this time we don't have an indicator variable, so we can't actually think of it as x equals 1 and x equals 0. The constant is given when this one occurs when L opening equals 0. But remember, this is the log of opening revenue. And so if we exponentiated that, that would be when the when the opening weekend revenue was equal to 1. So opening weekend revenue equals one unit. So it might have been, I'll say $1,000 if that was the unit. If we want to calculate a 95% confidence interval for the odds ratio in the general setting, we can now think this as the 2 steps that we did in the indicator explanatory variable setting. We construct a confidence interval for beta 1, so on the slope itself, which in this case, we get E1, which is 1.125 plus or minus 1.96. We're looking at 95% confidence interval, so Z star is equal to 1.96 times our standard error, which is 0.339. When we work out the endpoint of our confidence interval, we get minus 0.46056 and 1.789. And then remember, what we want to do is back transform to our original scale. So step 1 is confidence interval for slope itself. Step 2, we want to exponentiate it, i.e. exponentiate endpoints. In which case we get 1.585 and 5.986. So here you can also note when we look at this confidence interval, we have it as negative up to 1.7, it's covering 0. But what's actually important is that when we exponentiate it, does it cover the value 1? But we can see here that it does not include or cover 1. So this is actually a statistically significant covariate or effect in our association, I should say, in our regression model. To formally test that the null hypothesis that our slope parameter is equal to 1 against the alternative that it's not equal to 0, what we would want to do is, again, calculate our Wald statistic. So if we take the ratio of 1.125 over 3.339, and then we square it, we would get 11.02. So this is our Wald statistic. The degrees of freedom is equal to 1. And so our p-value, again, is this upper tail p-value given by the probability that a chi-square random variable with 1 degree of freedom is greater than or equal to our observed test value of 11.020. If we look at our table X, so I closed the book, I need to open it up again. Again, remember, we only are interested in degrees of freedom equals 1, so that's the very first one. What we can see, so the top row has to do with degrees of freedom equal 1, and what we see is that 11.020 will be somewhere between these two columns, the last two columns. So we know that our p-value is between 0.0005 and 0.001. So from table X, we get the p-value is bounded by this. From software, we get the p-value is equal to 0.001, at least rounded off. And so our conclusion is that the unit increase in log opening weekend revenue increases odds that a movie is profitable by about 3.1 times. And in a report or an abstract, often when we put in these results that include our model, we also include our p-value and the 95% confidence interval. So we estimate it to be 3.1 times, so the odds ratio with a confidence interval, 95% confidence interval, ranging from 1.585 to 5.986. Okay, so that's it. I went over a few minutes. Next day is our last lecture, and we'll finish off section 14.2. Closing comment, I did post solutions if you've been working through the odd numbered questions of chapter 14, and those are available on CourseLink in the same place that the chapter is available. Okay, see you soon. Bye.